To complete this video series, I have one final concept to share with you. If you would like to follow along, and I encourage you to do so, we're going to open the R script entitled CLT. There are many situations where the data distribution cannot be fit with the normal distribution model. Let's consider this manufacturing example. A manufacturing plant that produces bottles of 100 milliliters is allowed to have a tolerance of 2.5 milliliters. That is, the bottle can legally be between 97.5 and 102.5 milliliters and still be labeled as 100 milliliters. This is pretty common in manufacturing because processes are not exact. A certain tolerance must be allowed. Let's look at some sample data. Let's take a sample of 50 bottles off the assembly line and see what it looks like. Here's the histogram. This is a sample from what we call a uniform distribution, or a uniform model, where all values within a range, in this case 97.5 to 102.5, are equally likely. Remember how we would obtain a normal distribution and then compare it to the mathematical model? Well, let's do the same thing here. This is a sample of data, but let me show you what the mathematical model of the population looks like. This is the way the mathematical model for the population looks. Notice that the values range from 97.5 to 102.5, and the fact that the area is equal for every interval all the way from 97.5 to 102.5 means that any range of, say, 1 milliliter has equal probability. That's why we end up with this rectangle shape. The density is 0.2 for every point from 97.5 to 102.5 and 0 outside of those points. That is, nothing's allowed below 97.5 and above 102.5. So let's take again a single sample of 50 bottles. Knowing now that these are from a uniform distribution, here's what we get. This doesn't look like our last sample because samples vary. But if we took samples over and over and over again, we know that in the long run, we would get a uniform distribution. Let's try that. Here I'm taking 1,000 samples. I'm keeping track of all the samples, and now I'm going to look at a histogram. How about that? Just as in our previous examples, when you take many samples and keep track, you end up with a sample distribution, or a distribution of many samples, that looks like the population distribution. Now there's one step left I want to take. What if we create the sampling distribution of the mean when the underlying population looks like this, looks like a uniform distribution? What do you think we would get? Let's try it. Remember that a sampling distribution is a distribution of statistics. In this case, we're going to take a sampling distribution of the mean. So what I'm going to do is I'm going to take, now this time I've chosen to take 10,000 samples, each size 50. I'm going to record the mean for each one, keep track of those, and then when I'm all done, I'm going to plot a histogram of those means. Let's see what we get. Oh, eureka! Even though the original population distribution was uniform, the sampling distribution of the mean is normal. So everything we know about the normal distribution we can apply to this situation if we're dealing with the sampling distribution because it's normal. Isn't that wild? The original distribution is uniform, but the sampling distribution of the mean is normal. In fact, we can overlay a normal plot line. There it is. So even though the original distribution is a uniform distribution, the sampling distribution of means is a normal distribution. So we can use the normal distribution facts that we know about, things like p-norm, to find the probability of obtaining a sample with a particular mean. Let's suppose, for instance, we want to know the probability that the mean of the sample of bottles will be within 1/4 of a milliliter of the 100 milliliter target. So let's draw that picture. There's the normal distribution for the means, not the original scores, because the original volumes are a uniform distribution, but the means follow a normal distribution. And then we can look between 99.75 and 100.25, and we can come to the conclusion, again using p-norm, that 78% of our samples will have a mean that's within 0.25 milliliters, between 99.75 and 100.25 of the overall mean, which is 100 milliliters. Pretty cool, huh? We can use a uniform distribution of data and a normal distribution of means to calculate the probability where a sample mean might fall. So why did I call this file CLT? Because what we're looking at here for the first time is the Central Limit Theorem. The Central Limit Theorem says this: no matter what your original distribution of scores, no matter what the original distribution, whether it's uniform, normal, or something else, maybe something that's not even defined well by a mathematical model, the sampling distribution of means will be normal. That means we can always use the normal distribution in order to find a probability of where the mean might be, no matter what our original distribution looks like. That's the Central Limit Theorem, and that brings to a close this series of presentations. I hope you've learned much.